In this video, I want to talk about the idea of parallelism. We say that two lines are parallel if they have no points in common. So essentially they don't intersect, exactly what we think. And with this, I want to talk about the parallel postulate. The parallel postulate was actually Euclid's fifth axiom whenever he first did geometry in the Elements. And it was often believed that the parallel postulate shouldn't be a postulate, it should be something that we can prove to be true. And a lot of people tried, and it turns out that it can't. And by having different versions of the parallel postulate, we get different geometries. So let's look at the three versions. For the parallel postulate, we need to start with a line and any point not on the line. The first version, there exist no lines through that point A parallel to L. This is known as the elliptic parallel postulate. This gives rise to spherical geometry. The second version, there exists exactly one line through my point A that's parallel to L. This is the parabolic parallel postulate and gives rise to Euclidean geometry. And then the third version, there exist two or more lines through my point A parallel to L, and this gives rise to hyperbolic geometry, which I'll discuss more in a later video. Next, I want to define the idea of a transversal. If we have a line that intersects two other lines, it's called a transversal. So if I have any two lines, let's say these two here, and then I have a line that intersects both of them, this would be known as the transversal. And I'm going to label a few of these angles, 1 and 2 here, and then 3 and 4 here. Angle 2 and angle 3, right here and here, these are known as alternate interior angles. This is because they are on the interior of these two lines, and they're on opposite sides of the transversal. Angles 1 and angle 4 are known as corresponding angles. And this is because they're in the same corresponding spot on my two original lines. So if I think of these 4 angles here and these 4 angles down here, we're looking at things that are in corresponding spots. Finally, angle 2 and angle 4 are known as same side interior. They are on the interior of these two lines, and they're on the same side of the transversal. And equivalently, you can name a lot of other angles appropriately, such as same side exterior, alternate exterior, etc. The first thing I want to prove, if alpha is equal to infinity, so if I do not have a maximum possible distance, then parallel lines do exist. And in particular, if I have two lines that are cut by a transversal, such that the alternate interior angles are congruent, then the lines are parallel. In order to do this, I'm going to start with a line, which I'm going to call L, and any point A that's not on that line. I'm then going to draw the line AB, where B is any point on my line L. So pick any point on my line L and draw the line between A and B. I'm then going to pick another point F on this line L with F not equal to B. So any point on this line with F not equal to B. The next thing I want to do is construct a ray, AC. So this ray here will be C. On the opposite side of AB of F. So I don't want to construct it on the right-hand side for this particular picture. I want to do the opposite side of F, such that this angle CAB is congruent to FBA. So I'm constructing this so that my alternate interior angles are congruent. I then want M to be the line through the ray AC, so I essentially want to extend out this ray to a full line and call that M. We then have that the other pair of alternate interior angles are congruent, so this angle here and this one here, by the linear pair theorem. I know that CAB plus this angle have to add to be 180, and I know that FBA plus this angle have to add to be 180. And since CAB and FBA are the same, that tells me that these other set of alternate interior angles are congruent. Now that I have that alternate interior angles are congruent, let's suppose these lines actually meet, and we want to show a contradiction. So I'm going to draw a quick picture here. We have our lines here. Here will be L. We'll call this point here A and this point B. And this here is our line M from before, and we're claiming that they meet at a point W. And we'll go ahead and extend this out fully, line M out fully as well. Since we already know that alternate interior angles are congruent, we constructed it so that this angle here is equivalent to this angle here. Then we have a contradiction. By our exterior angle inequality, this angle 1 here is greater than the measure of angle 2, which is a contradiction since they should be congruent. So therefore, these two lines must be parallel, which gives me exactly what I needed. The first result of this, once again, if alpha is equal to infinity, so we actually have that parallel lines exist. And we know that our two lines are cut by a transversal here, such that corresponding angles are congruent. Then the lines are parallel. Well, this happens because vertical angles are congruent, so this angle up here is equivalent to this angle here, which then gives me my alternate interior angles being congruent, which gives me exactly what I need from my last theorem. In my other theorem, lines perpendicular to the same line are parallel. So if I have a line and I have some perpendiculars, such as these here, well then, since they're perpendicular, their corresponding angles are congruent, as well as alternate interior angles, which tells me that they also need to be parallel. And finally, I can give the beginning of one of my big proofs for spherical geometry. If alpha is less than infinity, so I do have a finite distance, which means I'll be in my spherical geometry case, the angle sum of any right triangle is greater than 180. So this is specifically going to look at right triangles instead of all triangles, but it is a start. If the legs of this triangle are less than alpha over 2, then Securi's theorem actually gives me the result. Securi's theorem told me that the angle sum is equal to twice the summit angle of a Securi quadrilateral, and we know those are obtuse angles, so we know 2 times an obtuse angle is going to be bigger than 180. So now we just need to show this is true if my legs are greater than or equal to alpha over 2. In this case, I'm going to assume I have my triangle. I'm going to assume the measure of angle C is my 90-degree angle. I know one of them has to be. And I'm going to assume that the leg BC is greater than or equal to alpha over 2. It could be that we have both of them, but at the very least we need one, since we've already proven the case that neither work. I then want to construct a point D on side CB such that the distance between C and D is exactly alpha over 2. And then I'm going to look at this side here, the segment between A and D. Then we have that the measure of this angle DAC is 90 degrees. And that's specifically because the measure CD is alpha over 2. We've proven before that if we have a point alpha over 2 away from a line, then every line we draw passing through point D is going to be perpendicular to that line. So every segment that I draw passing through D that intersects anywhere on line AC is going to give me a 90-degree angle. Then I have that the measure of angle A plus the measure of angle B is greater than or equal to 90. When I took angle A, I actually cut a small piece of it off to get an angle of 90 degrees. So I actually have my 90 degrees from angle DAC plus a little bit extra plus angle B. So that definitely has to be bigger than 90 degrees. So for my angle sum, I have something bigger than 90 degrees plus 90 degrees, which will be greater than 180.